Hi everyone. So today we'll just discuss the topic on force between two parallel conductors, torque on a closed circuit, boundary condition of a magnetic field. So force between current carrying conductors. We all know the equation F is equal to ILB sine theta. So that equation we are going to use it here. So here we are considered two parallel conductors, each carrying a current of I1 and I2. So we have two parallel conductors carrying a current I1 and I2, and when these two current are in the same direction, the conductor experience force of attraction. When they are in opposite direction, will experience a force of repulsion. Two parallel conductors which are separated by a distance d. So this d is the center distance between two parallel conductors, and we are just going to deal with the three-dimensional concept here. So AX, AY, AZ. Remember that this current element I1, it is in the direction of minus AX here. And similarly the distance D, it is in the direction of AY here. So we are going to have only two concepts here. One is AX, the current element is always in the direction of minus AX. That is what I have mentioned. I1 and I2 current is always in AX direction. But this distance is based on with respect to which conductor you are going to take. For example, if you are considering the distance from conductor A to B, so in such case, your D is going to have a vector of plus AY. It is in this direction. So AY. Suppose if you are going to consider the same distance with respect to B conductor, so it is from B to A. In such case, your D is going to be in minus AY direction. I hope you have understood. I'll repeat once again. I1, I2 current both are in AX direction, whereas D with respect to A, the D direction is in AY direction. With respect to B, it is in minus AY direction. So coming to the formula of H, we all know that a straight conductor, magnetic field due to a straight long conductor formula we have already derived, which is I by 2 pi R. So here instead of I, it is I1 2 pi D. So here we are going to consider what will be the magnetic field of a conductor. See the diagram. Magnetic field of a conductor A at point P. We are just going to find what is its magnetic field intensity. I'll repeat once again. We are trying to find what will be the magnetic field intensity, that is H at point P due to conductor A. So that is the first case. We are going to find it. For the second case, we are going to find what will be the magnetic field intensity at this particular point. Let me assume this point is Q. For this particular point, what will be my magnetic field intensity due to conductor P. So these are the two cases we are going to derive now. So for the first case, we are just going to find what is H of conductor A at point P. We are going to find it. So we are going to find what is magnetic field due to a conductor A at point P, which can be given by H1 is equal to I1, that current element, divided by 2 pi D. From the diagram we have just derived. So this equation is got from the normal formula, that is magnetic field intensity due to finite line conductor, which we have already derived. So it is I1 by 2 pi D. So I'll explain how we have written the direction minus AZ. Now coming to for finding this direction, I have just given a hint here. So we all know the Biot-Savart's law, basic law. So dH can be written as ideal into AR divided by 4 pi R square. Remember, your AR stands for the vector direction of the distance D. Ideal is your current element. So you all know that current element ideal is in AZ direction, that is minus AZ direction. We have already, minus AX direction, which is already given. And your dr represents the direction of D, distance D with respect to A. So it is in AY direction. So minus A cross AY will give you minus AZ according to your cross product rule. So I can say H1 is in minus AZ direction. So that is how I written. So, and we know that B is nothing but mu into H1. From this we can get mu. So since H is in minus AZ direction, B is also in minus AZ direction. So you can just implement this in B1 the original diagram. So your B1 is in minus AZ direction. So AZ here is positive, minus AZ downward. So this direction should be downward. So now we have understood. So we have calculated what is magnetic flux intensity at point P due to conductor A, that is B1 here. Similarly, we are going to find what is B2 here. So coming to the second case here, H due to conductor B at point P on conductor A is given by H2 by 2 pi d. And we know that current element, so once again we are applying the same rule here. So when you apply the same rule, your DL is plus AX and DL is minus AX, that doesn't going to change here, and AR is the distance from B to A, so it will change as minus AY. So you will get the equation as AX cross minus AY, so which is going to give plus AZ here. So this direction is going to be in AXZ here, and your B also is going to be given in direction A2 here. So that is how. So going back to the diagram, since B2 is in AZ direction at point Q here, so it is written upward here. So we have considered that. Now we are going to go for the force equation. So force on a current element A can be written as, we all know that force is IL cross B. So IL here is I1, this one I1, and here your magnetic field according to conductor A is P2. And similarly for conductor B, your current is I2, your magnetic field is going to be B1 here. So from the diagram we are writing as I1 L cross B2 for conductor 1, I2 L cross B1 for conductor 2. So we all know that this is in minus AX direction, and this is in your B2 is already we have derived, it is in AZ direction. So minus AX cross AZ will give you AY. So, and you know what is B2 equation, you can substitute it directly here. So it is L mu divided by 2 pi d. So you'll get this equation. Similarly, force on current element, coming to this I2L, once again it is in minus AX direction. B1 we already done in the earlier case, it is minus AZ. So minus AX cross minus AY will give you minus AY here. So we have force equation 1, which is in the direction of plus AY, another one in the direction of minus AY, but the magnitude remains the same in both the cases here. So I can say that when the current carried by both the conductors are same, the force is going to be in the opposite direction. So F1 in AY direction, F2 in minus AY. So they are going to be in opposite. So that is what we have seen. So when the current are in the same direction, there will be a force of attraction, which means that these are in opposite direction. And similarly, you can do the same condition when the current are in opposite direction. So by using the force equation, we'll just small torque on a closed circuit. And this is going to be very simple. So torque is nothing but force into radius. So R represents the radial, that is axial length, and F is the force on that axial length here. So I have considered a closed current circuit. So A, B, C, D. Remember, W stands for the width, L stands for the length of the conductor. So that is what I mentioned, L and W. And I have taken this direction as AX, AY and AZ. So your current element, this particular A, B. So you just see the current direction, it is from A to B, B to C, C to D and D to A. So for A to B, the current element, it is going to be in plus AY direction. And similarly, C to D, it is going to be in minus AY direction. So your magnetic field always moves from north to south. I have indicated the direction like this. So it is in AX direction. So your B vector, it is not going to change at all. It is in the direction of AX vector. Remember, your current element A to B in minus AY direction. For C to D, this current element, it is in plus AY direction. Now going to the force equation, force is nothing but, so first we are trying to find force and next R. So F into R will give you the torque equation. So F stands for IL B here, IL cross B. So for the first current element A to B, it is written as IL cross B, where IL is a vector of AY and B is a vector of AX, as I told already. So AY cross AX will give you minus AZ. So your resultant vector will be minus BLI AZ vector. And similarly for the side D, when you go for the side D, as I said before, IL is in minus AY direction and this is going to be in AX direction. So when you substitute it, you will get it as BIL AY. So when you now this is going to be multiplied with the R here. So for the A element, since your force direction is minus AZ, it is in downward. For the element CD, since your force direction is plus AZ, it is in upward direction. So based on that, we are going to derive the force torque equation. So torque is nothing but force into radius. So for this force element, and this is going to be your radial distance. Your radial distance can be written as the half of this width, which can be written as W2. Now your W2, it is going to be taken in which direction? This from B to C. So your B to C, when you consider, the direction is going to be in minus AX here. Back to the equation. So it is written as minus W2 by 2AX into your force equation, which you have already done, minus BIAZ. And similarly for the second case, for the section CD, it is going to be W2AX. We have to take the top portion of it into the width of the top portion into the force, which you have already derived. So AX cross minus AZ will give you minus AY, and similarly AX cross AZ will give you minus AY. Substituting, when you add these two equations, it becomes BILW minus AY, or else length into width can be written as area here. So your torque equation is BIA. So that is what from this you have understood. No, for AB we have just taken bottom portion of the radial distance, and for DA we have taken the top portion and we have derived the torque equation is this one. So from that, D is equal to BIA. It is a cross product, so we can also write it as BIA sine theta, because for a particular angle the torque can be given with this equation, or else we can write it as a IA cross B vector. So this IA stands for magnetic dipole moment, which is I into A here. So we have already seen in this electric circuit, electric dipole moment is charge into distance. Similarly, magnetic dipole is current into area. So remember this. So IA can be replaced as M cross B. So moving on to the boundary conditions. So boundary conditions, we all know that it is between B and H. So if we are going to consider two medium, so we are trying to find what is magnetic flux density and electric field intensity at the boundary here. And remember that for finding B, we just go for the magnetic Gauss law, that is closed surface integral of B into ds is equal to 0. And for finding electric field intensity, Ampere's law, so it is closed line integral of H into dl is equal to G. So the concept is similar to that of the electric field. So I have considered two different magnetic medium here, and So first medium, it is having a H1 resultant field which will be resolved into two component, tangential and normal, and second medium once again tangential and normal component. So first we'll go with the boundary condition for normal component, that is we are going to consider magnetic flux density. So flux density, a formula is integral of B into dx equal to 0. So I have considered a closed surface, so top, bottom and lateral, and we know that lateral portion del H is 0, so this part becomes 0. Only for top and bottom we are going to consider. When you consider for top portion, always remember flux leaving the section we'll consider as plus here, flux entering will consider as minus here. So from here, so the flux leaving will be taken as so this flux is perpendicular to the surface, so that can be considered, and similarly this flux Bn2 is perpendicular to this particular surface. So when you consider that, will the equation, that is Bn1 del S minus Bn2 del S is equal to 0. From this Bn1 is equal to Bn2. And next is tangential component for finding that Ampere's law. So line integral of H into dl is equal to I here. So when you are considering a closed path, we can go for A to B, B to 1, 1 to C, C to D, and 2 to D, and 2 to A here, which is equal to I. So when you go for this law, A to B, when you consider a dl stands for the length, and H stands for the tangential magnetic field along the length L here. So we go one diagram here. So you can just see for this AB section, your tangential magnetic field is HT1 into del W, and for the portion B2 1, I'll consider this as B2 2. When you go for this one, it is minus Hn2 into del H by 2, and similarly for this portion it is minus Hn2 into del H by 2. So whatever we have done in electric field, the same concept is applied. So you can substitute all the equation, and at the boundary del H tends to 0. So when you substitute del H tends to 0, all the component becomes 0, only Ht1 del W and minus Ht2 del W is equal to I. So now I am considering no current in the closed path here, so it becomes 0 here. So when you substitute the equation here, you will be getting that as Ht1 is equal to Ht2. So for boundary condition here is the normal component of your magnetic field intensity are equal, the tangential component of electric field intensity are equal here. Thank you for watching the video.